All right, our first section here is going to be lesson A1. That's the appendix section 1, which is on radicals and rational exponents. You'll find this in the back of your book, the appendix sections. So, you've worked with radicals before, maybe not to this depth, but we're going to get right into things. Definition of real nth root of a real number. Let n be an integer greater than 1, and a and b are going to be real numbers. So, we're going to have, if we have b to the nth power, that's an exponent n, is a, then b is the nth root of a. So b would be the nth root of a, and a would be the nth power of b. So if a has an nth root, the principal nth root, so principal nth root of a is the nth root having the same sign as a. So we do have to be careful about all of our signs. Principal nth root of a is going to be denoted by the radical expression, the nth root of a. You've seen square roots, you've seen cube roots. These mean the same thing. So nth root could be any index. The positive integer n is the index of the radical, and a is the radicand. So that's what we're trying to find multiple powers of. Special notes are, if n is odd, every real number has exactly one nth root. So if this is odd, there's exactly one answer. If n is even, two things could happen. First, if a, the thing under the radicand, is positive, and again your index is even, could have two possible roots. I'll get to why in a moment. Otherwise, if a is negative, you're trying to take, let's say, the square root of negative 25. There's no real answers, so there will be no real nth roots. You could have complex answers, but we're not going to get into that for right now. You'll get into that later in the course. So, let's actually see this in action. First example, finding the principal nth roots. So, this is asking, I don't see anything in my index here. If we don't see that, that always means the square root. You've seen that before. Technically, there is an index of 2. So, the square root of 36 is what times itself is 36. Well, that's a positive number with an even index. So technically there are two answers, but we're looking for the principal root. So I'm looking for the positive answer because 36 is positive. That just ends up being 6. In part B, we have the cube root of 27 over 8. Nice thing about fractions is you can split it up. We're actually going to get this more as a property down here, but we can think of this as the cube root of 27 over the cube root of 8. Now I'm asking what times itself again is 27? Well, that's got to be 3. What times itself again is 8? Ends up being 2. If you don't believe me, you can type that into a calculator, cube it, and you get back to 27 over 8. Now, part C is very similar. We've got the cube root of negative 27 over 8. Well, if we remember this statement from above, the cube root of a negative value, it's an odd index, so that means we're always going to have an answer, and it's going to end up being the same value as we have here. So, don't think too hard. We already found the answer. It's just negative 3 halves. That's because if you take negative 3 halves times negative 3 halves times negative 3 halves, you end up with exactly negative 27 over 8. Last one is the fourth root of negative 625. Well, I have an even index, and I'm trying to find what times itself is negative 625. Let you think about that for a moment. Yeah, there's no way to do it. There's no way to take 4 of the same thing and multiply it by itself and end up with a negative value, because a negative times a negative ends up being positive. Positive times a positive is always positive. And I'm not mixing positives and negatives because they're different numbers. So this does not exist. So keep that in mind. Now, we do have a whole bunch of different properties that we can utilize to simplify things when we're working with our properties or working with radicals. One thing that is really handy is the nth root of u times v. And so if we have two things that are being multiplied under the radical, we can split it up. Now, this often comes in handy the most when we have something that isn't a perfect root, such as the square root of 75. There is not a single thing times itself that equals 75. So one thing that we can do is split this up into a perfect square, meaning the square root of 25. And then what else do we have to multiply by to get 75? It's got to be a 3. So square root of 25 times the square root of 3. Well, we know the square root of 25. That's pretty easy. That's just 5. Square root of 3, there's no way to split it up, and there's no nice answer to that multiplies by itself to get to 3. So that's actually an irrational number. I'm just going to leave it as is, root 3. So the square root of 75 can be simplified to 5 times the square root of 3. There's other ways that we can simplify this stuff as well. I'll get to that in the next example. So we can split up multiplication. We could also combine them and go backwards if need be. But here we can split up division. We saw this above as well. I'll have another example here. We have the 4th root of 96 over the 4th root of 6. Well, I'm going to start with the easier side. What times itself times itself times itself is 6. Nothing comes to mind, and it shouldn't because it's not a nice number. Same thing's going to happen with the 4th root of 96. So this is where I said we can go backwards. We're actually going to combine this and give us the 4th root of the whole fraction, 96 over 6. We can simplify that, and that actually becomes the 4th root of 16. Now, if you ever come across a 4th root, a nice quick trick that you can actually use is to take the square root twice. It means the same thing. So what's the square root of 16, I just gave you the answer, is 4. And then the square root of 4, again, gives us 2. So the 4th root of 16 is just 2. Now, technically, I am working with all positive integers, but this could be plus or minus 2, just as an FYI. Next example is if we take multiple radicals, let's say the 3rd root and then the 4th root of a number, we can simplify that down to a single root where we just have and multiply the indexes, or indices, I should say. This comes from the fact that radicals are basically the same as exponents. And what happens when we take an exponent to an exponent? We multiply the powers. So same thing's happening here, and our example for this is what happens when we take the square root of the cube root of 7. Well, we're not going to get a nice answer for this, but that's okay. One way to simplify this, because that's just ugly and gross, is we take the square root, which remember is index 2, and we multiply it by my next index. 2 times 3 gives me the 6th root of 7. Now, unfortunately, that's as far as we can go because 7 being a prime number, there's no way we're going to be able to multiply 6 things to get to it. Not going to work out. Next one is what happens when we take an index, any index, and raise it to the same power. Well, we can think of that as basically raising it to the first power because some things we'll get to soon in class. So, for example, the 4th root of 5, all to the 4th power, they technically end up canceling each other, and you end up with just 5. So it's a nice way. How do we get rid of radicals? We can take, or the square root, you always square it. If you have a squared, you take the square root of it. They are inverses of each other. Next example here, or next property, is what happens when we can when we have an index and a power, we can technically swap them. Sometimes it's really handy to do that. So if we have, I'm running out of room here. If we have, for example, the cube root of 27 squared. Now, I'm going to say you can do that in your head, but not the way it's written right now. What we actually want to do is use the property and switch our where my power is, because I don't know what 27 squared is off the top of my head, nor do you have to. There's an easier way to do this. If we swap it, it's going to end up being the cube root of 27, and then we square it all. Well, the cube root of 27, we did that earlier. That's what times itself again is 27, and that ends up being 3. That I can do in my head. So this is 3, and I'm still squaring it. The power is outside. 3 squared is just 9. So it's a whole lot nicer to take the radical first, because it gives you a smaller number that you can then work with the power later on. Because 27 squared, big ugly number, then you have to figure out what times itself again is equal to that, and that just ends up being 9. So this is a whole lot easier way to do it. Lastly, another thing to notice this is very close to what we did before. Be careful if we have a power to another power. For example, we have the square root of -6 squared. Well, that's going to end up equaling, here, my radical, or the index is even, my power is even, so the end value is even. I just end up taking the the absolute value of the thing inside. So that ends up being the absolute value of -6, which is just +6. Whereas on the other hand, if we took the cube root of -6 cubed, these just really end up canceling, and it ends up being the number that you would be dealing with anyways, which is -6. So keep that in mind. Let's do the last couple examples here, and we'll do the back in a separate video. So last couple examples, how to actually remove factors from radicands. The index is really what you want to focus on. So first, take note, it's even. The thing under the radical is positive, so that means we can work with it. That's a good thing. It's not like the fourth root of -625 that we had above. So what I am doing is trying to find 4 of something that is hidden in this 80. So what I like to do in this case is actually break down my 80. Break it into, let's see, when I say break it, I'm going to make a factor tree. So what multiplies to 80? There's a number of ways you could do this. I'm going to go with 8 and 10. I can break down both of these, so I can go further. 8 is 2 and 4. I can't break down 2, so I'm going to highlight that or underline it. 4 I can break down into 2 and 2. And then 10 can break down into 2 and 5. I can't break down either of those, so they're both underlined as well. So what this really means is when I factor 80, I can factor it in always a unique way. Go as far as you can with this. This ends up being the fourth root of 2 times 2 times 2 times 2 times 5. So those are all of the things that I underlined there. That's, if you don't believe me, multiply these back out. You get it back to 80, guaranteed, every time. So what I'm really trying to do in this is find a perfect fourth root. And for that, I need a group of 4. And right now I see 4 2's. So there is a group of 4 2's. Now, in order to actually simplify this, technically that would be like the fourth root of 16 if I multiplied all those out. And we did the fourth root of 16 before. That ends up being just 2. So what happens is I take one of those 2's out of the radical. So that is now outside of the radical. And I sort of think of it as the rest of the 2's had to help that friend get out. They were used up in the process. Unfortunately, they go bye-bye. So they used up in the process, but they got one of the 2's out. It's really hard to get a friend out when you're in a fourth root. Now, what's left over, what's still stuck under the fourth root, is anything that we didn't actually highlight or underline there. So that's got to be this 5. So we still have the fourth root of 5 left over. This means the fourth root of 80 is the same as 2 times the fourth root of 5. Notice the 2 has nothing to do with the radical anymore. We're just multiplying by the fourth root of 5. So that's part A. Part B, I'm still looking for, in this case, 2's. Must have 2's. Now, there's going to be something extra in this that I'll get to momentarily, but I want the square root of 18x to the 5th. I'm going to break everything down. 18, I'll do this off to the side. 18 is, let's see, 9 times 2. I can't break down 2, but I can break down 9. That's a 3 times 3. Both of those 3's I can't break down any further, so I'm going to write that here. This is 3 times 3 times 2. That's how to get back to 18. And then what does x to the 5th really mean? Well, a power just means that we're multiplying it by itself that many times. So this ends up being x, 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 x. 5 of those. And back to my index. It's a 2. I didn't write it this time because it's implied that it's a square root. I'm looking for pairs of 2 or groups of 2 now. I see a group of 2 3's. I don't have a second 2, so I'm not gonna circle that or anything. I have a group of 2x's here and a group of 2x's here. Now, like before, they need a friend to be able to get out of the radical. So 1 3 comes out, the other 3, the friend, is left behind. 1x comes out, 1x comes out. Now, what did I actually pull out of the radical? I pulled out a 3 and 2 x's, but remember we're multiplying, so that's a 3x squared. And what's still left over is a 2x. So, there's one other thing that I need to keep in mind here, and it's because this was an even index. If we go back to that very last, the last property from above, that said what happens when we have an even index and an even power? We need to take the square root of whatever we're taking out. Now, I didn't do that before because it's a 2. Do I have to take the square root of 2? No, it's still 2. Here, I took out a variable. That's a problem. I don't care so much about the 3 because for the same reason, square root or absolute value of 3 is 3. But I don't know about variables because variables could be any number. It could be positive. It could be negative. So, one habit I want you to get to start here is anytime you take a variable out of an even and only even indexed radical, put absolute value bars on it. Now I'll say one final note. In this case, specifically this case, it doesn't matter. Why? Because x squared always ends up being positive. So technically, in this case, I don't need them, but that's okay. If you keep them there, I would never mark off points for that or anything. But get in that habit. It'll save your butt on tests, quizzes, anything. And it's always good to keep in mind. So now that I just said that, we're going to apply the same concepts here. Part C, we're taking the fourth root of x to the 4th, y to the 4th. I'm not going to write all of this out because x to the 4th means 4 x's in a row. Y to the 4th is 4 y's in a row. And how many are we? How large of a group are we looking for? We're looking for groups of 4. So I know I can have 1 from there and 1 from here. That's going to be an x is out of the radical, a y is out of the radical. They're variables, and this is an even index. So I'm going to tack absolute values right around those, and we'll be good to go. Now, there's nothing left under the radical, so that is literally just your answer. I'm going to do one more, part D, cube root of negative 24y to the 6th. I'm going to break down 24. That's let's go 4 and 6. 4 is 2 and 2, 6 is 2 and 3. So, I have a negative. That's okay, because I have an odd root now. So I'm just going to take out that negative once I get to this step. Now, I broke down 24 as 2 times 2 times 2 times 3. And then I have 6 y's. So that's 1, 2, 3, 4, 5, 6. All of that is under the cube root this time, so I'm looking for groups of 3. There's a group of 3 2's. There's one group of 3 y's, another group of 3 y's, and I am going to take out this negative. Why? Because technically, I have a negative 1 times a negative 1 times a negative 1. I can always do that when I have an odd index, not even. So technically, that I can write that as 3 negatives and just pull it out. So negative comes out of the radical. I pulled out 1, 2, and let's see, 2 y's, so that's y squared. We're multiplying. And what's left is a 3. That's it. There you go. So that's your fully simplified answer. I'm not using absolute values here because this is odd. X is odd. So that is your final answer